some recent work that I did with Matthias, Tom, Kambiz, and Daniel. And it's about learning from quantum data. So in particular, we were thinking about generalization behavior of quantum learning algorithms. And I'll describe what that is soon. My outline for the talk is I'll first establish some background about classical machine learning, supervised learning in particular. And I'll introduce the notion of generalization and how we capture this quantitatively. And then I'll go on to describing how we might think about quantum learning algorithms from the point of view of generalization. And our contributions in this direction are sort of threefold. So I want to convince you first, as I present the background, I also want to convince you that it's quite subtle to talk about generalization for quantum learning algorithms or when quantum data is involved in particular. And so the first thing that we had to do was establish a framework for modeling quantum learners that could capture the notion of generalization. And then we generalize some classical information-theoretic bounds on the generalization error to the quantum setting. And we also have some applications of this framework and these bounds that we developed to some settings of quantum learning. So I'll get straight into it. So I'm sure most of you are familiar with learning theory and the notion of supervised learning. So what happens in supervised learning is there are going to be two phases. The first phase is you have a learning algorithm and it receives some data as input. And this data is usually going to be sampled identically from some underlying distribution that I call mu. And it's coming from some instance space Z. So each Zi is drawn from some instance space Z. And what is the algorithm going to do at the end of its training process? It's going to output a hypothesis. So for example, you can think of this hypothesis as the weights of a neural network or something similar. And the learning algorithm itself, for this talk, I want to think of it as a randomized algorithm. So effectively, it's taking a data set, which is a random variable, and it's going to map it to a hypothesis. So it's essentially a conditional distribution, taking data sets to hypotheses. And this conditional distribution is parameterized by the learner. So like whatever the learner is actually going to do, for example, it might be doing some gradient descent, or in this case, in fact, because we want to think about randomized algorithms, the internal randomness could be coming from the fact that you're performing stochastic gradient descent. So the learning algorithm itself is effectively a channel that maps training data to hypotheses. And you can think of that as a conditional distribution, essentially. And this also induces a joint distribution over the space of hypotheses and data. So that's effectively straightforward. And the second phase of learning is testing or inference. So once the learning algorithm has had the chance to use its input data to develop a hypothesis, it's going to be tested on some new data, some unseen data, but it's going to come from the same distribution. So we independently sample a new instance from the same underlying distribution. And we want the learning algorithm to output the whatever it thinks should be the right action on that instance. So because we're talking about supervised learning, for the most part, you can think about Z as being a Cartesian product of some instance space X, which could be, for example, images, and some space of labels Y. So this could be the cliched example of cats and dogs. So X is images and Y is labels, cats and dogs. And the space of hypotheses in this setting would be functions from X to Y. And so when the hypothesis is being tested, it's going to get a new X, which is a new image, and it has to output the correct label for that image. So one of the central questions in learning theory is whether good performance in the training phase implies good performance on unseen data. So we want learning algorithms to generalize well. So because at the end of the day, it's not only that we want to fit the data that we have at hand, we also want to be able to make good predictions on unseen data. And this is the main question that we'll be talking about in this talk. So to go further, in order to design a learning algorithm, we need to talk about some notion of loss or some kind of way to quantify how well the learner's hypothesis is performing. And this is done using a loss function. The loss function is going to take a hypothesis and an instance, and it's going to output a real number, a positive real number. And this number, you can think of this as a loss or a penalty. So if the number is very large, it means the hypothesis is performing poorly on this instance. And if it's small, then it means that the hypothesis is quite good on that instance. And for an example, there's the standard sort of, L2 loss. So if again, if the instance space Z consists of images and labels, X and Y, the hypothesis could be a labeling function. It's a classifier. And the loss is then going to be just, W of X minus Y absolute value squared. So the optimal hypothesis, typically the optimal hypothesis that we're interested in, is going to be the one that minimizes the expected loss. So remember, there is an unknown distribution mu over the instances. And over this distribution, I can take so if I fix a hypothesis W, for this hypothesis W, I can evaluate the loss function over any instance Z. And if I take an expectation of that, this is called the true risk because it's taken over it's the expected loss taken over the true underlying distribution. And the optimal hypothesis is usually going to be the one that minimizes this expected loss, this expected true loss. But in a realistic situation, we don't have access to mu itself. So we don't have any knowledge of the underlying distribution. So instead, what we do is we minimize the empirical risk. So from the first slide, if you recall, we have a data set S consisting of n identically sampled points from mu. Using this, we can define an empirical loss, which is just the sample average of the loss. So because I introduced some notation here, this R hat, I use hat for empirical, and the subscript S is to indicate the data on which the empirical average is built. And so for a fixed hypothesis W, I have the empirical loss R hat S of W, and I have the true loss R mu of W. Okay, so empirical risk minimization is the most common kind of learning procedure. So because you don't have access to the true loss, you minimize some kind of empirical proxy for the true loss. Okay, so the learner's hypothesis at the end of all of the training process, the learner's hypothesis is some W. And this is also going to be a random variable. As I said on the first slide, the learner itself is randomized. So there is some distribution over hypotheses that it induces. And over this distribution over hypotheses, so what we're interested in is the average behavior of the learner. So suppose we perform the whole learning procedure multiple times with a different data set each time. Then on average, you can talk about the expected empirical risk of this learning algorithm. And that's the expectation over this joint distribution of hypotheses and data that's induced by the learner of the empirical loss. And in the literature, this is often called the training error. So it's the expected empirical loss that's called the training error. And we have another quantity that's the expected true risk. So we had the true risk R mu of W that's defined as an expectation over the actual underlying distribution mu. And suppose we perform the learning process. So we have a data set S, we perform the learning process, and the learners produced a hypothesis W. If we now sample a fresh point, because this is what we wanted to do, right? In phase 2 of the learning process, in the inference or the testing phase, we want to draw new unseen data. So this unseen data is independent of the learner's hypothesis and everything else that happened before. So we have an expectation over this distribution over hypotheses of the true risk of the underlying learning problem. And this is called the testing error. So in some sense, the training error is empirical. It's dependent on the data set. And the testing error is quote unquote true because it comes from the learner's hypothesis being evaluated on an independently sampled unseen data point. And I just want to highlight that we can rewrite this. So if you recall from the previous slide, this quantity R mu of W is this expectation over here. So if we can simply rewrite this by using the fact that the empirical risk converges to the true risk. The empirical risk's expectation is actually equal to the true risk. So using this, we can rewrite this in this form. And this will turn out to be useful in a moment. So this is actually a very simple but insightful rewriting that actually underlies a lot of the classical theory of generalization. Okay, so what I'm building up towards is trying to define generalization. So trying to quantify how we can understand the behavior on testing data by knowing something about the behavior on training data. So a good learner, as we saw on the previous slide, for example, empirical risk minimization, minimizes the training error. So as we said, the learner cannot evaluate the true risk. It only evaluates the empirical risk, and it minimizes this. And the hypothesis that it produces is a good proxy for the true optimal hypothesis. But in fact, it's not only the training error that we want to minimize. Because if you think about it, if you minimize only the training error, what you're doing is adapting very well to the training data. And this doesn't necessarily mean that you adapt well to the underlying distribution over data. So you may fit too much to the training data, and your performance on unseen data will suffer. So what we actually want is, of course, we want small training error. So that's the second term here. But we also want, we actually want small testing error. So what we actually want the learner to do is to perform well on unseen data, because we're interested in making predictions. So just, by trivial rewriting, the testing error can be thought of as the testing error minus the training error, the difference between the two, plus the training error. So we know that empirical risk minimization is already minimizing the training error. So we don't need to think about that anymore. But what's important now is this term in blue here, the difference between the testing error and the training error. Minimizing this can give us some handle on generalization. So it's telling us something about how, what the learner's getting out of training is carrying over to the testing phase. And indeed, this first term, in expectation, so based on the two quantities that I've defined above, in expectation, this quantity is called the expected generalization error. So I have this star definition here at the bottom. So on the bottom line, if you look at this is the expectation over the joint distribution over hypotheses and data that's induced by the learner between the empirical risk and the true risk. So as I've written here, what we want is to minimize the difference between the empirical risk and the true risk. We want to do this in expectation. So we want it to be the case that on average, the learner performs well. And the first line here is just a rewriting of the second line using the insight that I pointed out here. So if we rewrote the testing error in terms of the empirical error, then we have the first line here. And I just want to point out that on the first line, you'll notice that both these terms, the training error and the testing error, have the same functional form. So the object of which we're taking an expectation is the empirical risk. But what's changing is the expectation itself. So for the empirical risk, the expectation is over the actual joint distribution between data and hypotheses. Whereas for the true risk, the expectation is over independent copies of W and S. So as I was pointing out at the beginning of the slide, in the testing phase, we draw an independent instance, an unseen instance that's independent of everything that happened in the training phase. And we test the learner's hypothesis on this new data point. And what that's essentially saying, the intuition is that this means we're testing independent copies of data on the hypothesis, or rather testing a copy of unseen data a copy of independently sampled unseen data on hypothesis that's been produced in the training phase. So are there any questions so far? Because this is the classical setting, and everything that happens going forward will build on this. Okay, so maybe I can proceed. So controlling the generalization error, so controlling this quantity. By controlling, I mean having a way to bound this quantity. It gives us a way of avoiding overfitting. So we're ensuring that the training error is close to the testing error, which is somehow capturing the fact that the hypothesis is not simply fitting to the training data, but it's also performing well on unseen data. So it's actually capturing something about the true underlying distribution and not just about the empirical sample that it's received. Okay, and this has been one of the sort of major quests in learning theory, figuring out ways of bounding, so theoretically bounding the generalization performance of learning algorithms. And many methods have been developed to do this. And quite recently, one of the methods that's been developed is based on this idea of decoupling. And by decoupling, what I mean is the following. It's what I was explaining on the previous slide. So the expected empirical risk is the expectation over both the hypotheses and the data. So this is a joint distribution induced by the learner over hypotheses and data of the empirical risk. So this is the second term here that I've written in red. This is the empirical risk. In going from the empirical risk to the true risk, which is what we want to do, right? Because the empirical risk represents the training phase and the true risk represents the testing phase. So in going from the first to the second quantity, there's some kind of decoupling of the two variables, S and W, that happens. So in the testing phase, we have a hypothesis that's been produced in the training phase, and we have an independently sampled data point that's coming from the underlying distribution. So we have independent copies of S and W that I've denoted by S overline and W overline here. And as we saw on the previous slide, we can re-express this expectation, so the one over here, the first term over here, in terms of the empirical risk again. But the crucial difference is that this is over the product distribution between the hypotheses and the data. So let me just flip back to the previous slide for a second. So if you notice the definition of generalization that I have here at the bottom, the first term is the expectation of the empirical risk over this product distribution, and the second term is the expectation of the empirical risk over this joint distribution. So effectively, what's happening when you go from the first quantity to the second is that the hypotheses and the data are being decoupled as random variables. And based on this idea of decoupling or change of measure, Xu and Raginsky in 2017, and also Russo and Zhu in 2019, presented a way of bounding the generalization error for a very large class of learners and data in terms of mutual information. So it's the mutual information between the hypotheses and the data that's going to matter. So exactly what did they prove? If the learner uses a loss function that is well-behaved in some sense, so they assume some kind of tail bound for the loss function. I'll come to that in a minute. Then for these well-behaved learners or well-behaved loss functions, the generalization error of the learner relative to the underlying data distribution can be bounded by the mutual information between the hypothesis and the training dataset. So from the first slide, if you recall, I mentioned that we want to think about the learner as a channel. So it's a channel that's mapping one random variable, the dataset S, to another random variable, the hypothesis W. So this channel has some mutual information between its inputs and outputs. And what's really nice about this bound is that it gives us an intuitive way of understanding what's going on in the learning process. So if the mutual information between the hypothesis and the data is very large, that means this bound is large. So the generalization error is potentially large. What that means is that the way you can interpret that is that the hypothesis somehow has extracted too much information from the training data. So the hypothesis has adapted too much to the training data. And in some sense, this reflects overfitting. So what we actually want is to design algorithms, and the design of a learning algorithm involves the appropriate choice of loss function, etc. We want to design A such that this mutual information is not too large. And if we're able to do that, then for this class of learning algorithms, that by itself sort of ensures that you have good generalization behavior. And I should mention what these tail bounds on the loss function are. So what we want is for every fixed hypothesis, if we think about L of WZ as being a random variable, because Z itself is drawn at random from the distribution mu, we want that random variable, L of WZ, to be sigma sub-Gaussian. And a sigma sub-Gaussian just means that the tails are sort of bounded by a Gaussian that has variance sigma. So for such loss functions, which have good tail behavior, we have this kind of information-theoretic generalization bound. So again, are there any questions at this point?
I ask a basic question
Yes.
without knowing?
Yes, please.
Why is it bad to have more mutual information? Shouldn't that be what you want, to extract as much information as you can from the training set?
Right, yeah. So we do want a lot of information from the training data set, but I think the idea in general in learning is usually that you're trying to learn some, let's say, low dimensional function from a lot of data. So the data itself could be in a high dimensional space, and you're trying to extract some, for example, if we're thinking about binary classification again, the objects could be in a very high dimensional space, but you're only interested in some kind of one-dimensional behavior. So if you, for example, if we were thinking about something simpler, if we were thinking about polynomial interpolation, and you have, let's say, 10 points, and you try to fit it with a candidate function that has 10 degrees of freedom, you're sort of going to fit all the training data perfectly, but there's going to be too much variance, right? So what it's trying to intuitively capture is the fact that there is enough information in the data, but there's also too much information. There's more than you may need. And somehow controlling how much information goes from the training set into the hypothesis is allowing you to generalize better, because the training set contains some information that's perhaps spurious when you take the whole distribution into account. When you take the actual underlying distribution on data, it may have properties that are not very well represented in the training set. And so we want to avoid capturing too much information from the training set. Does that make some sense?
Yes, but then why is mutual information like a good account if you're talking about dimensions being the problem or something?
Okay, yeah. So so that could potentially become clearer if so mutual information can then be related to entropies, and this will depend on the dimension. So you can get a so this bound can potentially be quite sharp, but you can get a tighter looser upper bound on this quantity itself by replacing everything with entropies, and then replacing the entropies with some logarithms of the dimensions. So in some sense, it can ultimately be bounded in a loose way using the dimensions.
Okay, thank you.
Okay.
I have a question also.
Yeah.
That was a very good explanation, but so this gives a very information-theoretic perspective to the bias variance trade-off.
Yeah.
But in real life, this is not what happens, right? So some people would say overfitting is not bad. You're saying overfitting is bad. So does that mean you don't mean the same thing under overfitting?
Okay. Again, right. So I'm not necessarily saying that overfitting is bad, but I'm saying that we may want to have some way of controlling overfitting. So one way to control overfitting is parameter counting. And this kind of information-theoretic bias variance trade-off provides another handle on overfitting. So it maybe gives you a way of measuring how much you're overfitting to the data. And perhaps if you, after you perform your training phase and you do some testing and you realize that you're overfitting, then maybe you can go back and tune the algorithm to overfit less using some, some insights from these bounds.
Thanks.
Okay. Maybe I can proceed now. So this was this work of Shu and Roginski was quite, it inspired a lot of follow-up work, and it was an important, it was important progress in the field. For one thing, it provided sort of data-dependent bounds on the generalization era. So most of the previous bounds, so almost all the previous bounds that we have in learning theory, were based on dimensions. So they were based on things like the VC dimension or shattering dimensions. And these things capture the worst case behavior of the class of functions you're trying to learn. Whereas, and also they don't take into account the actual data that's being used for the learning problem. So these bounds, in contrast, take into account exactly what the learner is doing. So, the actual loss itself and this mutual information is intrinsically somehow related to how the learner performs its learning process, how it outputs a hypothesis. And in addition, this is also dependent on the data itself, which is quite nice. So it's somehow moving towards more practical settings. And it also provided, so if you're familiar with these notions of differential privacy, then it also provided a new notion of stability. So you could talk about a learning algorithm being stable if it has small mutual information. So small perturbations in the data set, if you repeated your training process with slightly different data each time, the hypothesis is not going to vary very much, or at least the generalization behavior of the hypothesis is not going to vary very much. And there's been a lot of follow-up work that generalizes this to larger classes of learners, different kinds of assumptions on the loss function, and even to out-of-distribution generalization. So if the testing phase happens on a distribution that may not be mu, but the unseen data is coming from some slightly drifted distribution, that's called out-of-distribution generalization, and it's also quite relevant in practice. So there's a lot of follow-up work that's been trying to generalize these these bounds to those settings. Okay, so essentially this work was a very important point in learning theory of generalization. And what we try to do in this work is to pick up this intuition, this piece of work, and see how we can take these notions to the quantum setting. So there's been a lot of work on quantum learning theory, quantum machine learning, and because generalization and average case performance is quite important also in the quantum setting, we wanted to address what generalization should mean if you had a quantum learner that's potentially using quantum data and potentially even producing a quantum hypothesis at the end of its process. And in fact, we realized that even defining the notion of generalization was quite subtle. And I'll try to convince you of that in a few slides. And once we established a framework that could talk about the generalization of quantum learners, we wanted to then see if the generalization of quantum learners can be bounded similarly to the work of Chu and Roginski by, the obvious or natural thing that you would think about is the quantum mutual information. So can quantum information theory and quantum information-theoretic quantities be used to bound the generalization error of quantum learners? So these are the two questions that we addressed in this talk, in this work, and that I'll be also addressing in the talk. And in this direction, we have essentially three sort of contributions. So first, we describe a rigorous framework that can capture perhaps the most general kind of learning algorithm. So a learning algorithm that takes a combination of classical and quantum data, and it performs some combination of classical and quantum post-processing and outputs some potential combination of classical and quantum hypotheses. So of course, you could think of everything as quantum, and that would also just if you restrict it to diagonal density matrices or something like that, then that would also capture the classical setting. But it turned out to be easier and more intuitively clear to describe everything as being a combination of classical and quantum data. And then within this framework, we were able to prove quantum information theoretic generalization bounds. So quite analogous to the Chu and Roginski result that I showed you. We proved that quantum learning algorithms, given some assumptions on how the loss functions behave, can also achieve good generalization behavior in a way that's sort of mathematically provable. And then we also have some applications to different kinds of learning problems where our framework and our bounds can apply. So we were able to, rederive some existing results in the literature. So for example, PAClearning of quantum states. And we were also able to prove some new results. So for quantum differentially private learning and things like that. And I'll come to that in a couple of slides. Okay, so to start off, the first thing that we need to establish is what exactly is a quantum learner and what is the data that it's going to be learning from. So as I hinted on the previous slide, the learner is going to use a combination of classical and quantum data. This classical and quantum data is, so as in the classical case, you could have some data set S that consists of n points from some underlying instance space Z as we had before. And this S is sampled identically from this underlying distribution mu. But now in addition, for each such classical data point S, we also have some kind of quantum state rho, some quantum information that's being passed on to the learner in addition to the classical information. And we capture the whole thing by this classical quantum data state. So the data state consists of, for each classical data point S or classical data set S, there's some quantum state rho of S. And this expectation just represents this, the fact that this state is actually being drawn according to some underlying distribution over mu, over Z. And so mu is the classical data distribution. And this data state could live over some Hilbert space. I haven't really specified what this Hilbert space is at this point. It could be, qubits, some dimension D Hilbert space, or it could be anything that depends on the actual learning problem. So once you have this classical quantum data, we need to talk about losses and what the actual process of learning is. So in the learning process, the learner has to use its training data to come up with a hypothesis. And in order to refine this hypothesis, it needs to test it. It needs to evaluate the loss that a candidate hypothesis incurs on some data. So it needs some data to come up with a hypothesis, and then it needs some more data to evaluate that hypothesis. So in the classical case, yes.
So can I ask a question?
Yes,
so,
please.
So, like, what does it mean now to, like, if you want to test your algorithm, then there should be another data point arriving, but sort of all these, so the row depends on a whole string S, and so on. So we have like one more classical sample, then what does it mean for the goal to increase? Sort of like you should have some row attached to it as well, like some row of S attached.
Yes, exactly. That's how we conceptualize it. So every classical data point. So okay, depending on the actual problem you're addressing, the classical data could be vacuous. So you may not need any classical data, or the setting can also capture the case where there's no quantum data and you're just purely in the classical setting. But in principle, in the most general kind of setting, it's exactly as you described. So once the learner has performed some training and come up with a hypothesis, in order to evaluate that hypothesis, it needs some more data. So it needs some combination of S and rho again.
Okay, maybe let me rephrase the question. Like, shouldn't the state be like a n-fold tensor power of some rho?
Oh, yes. Yeah. Okay, that's a very good point. Sorry. Yeah, maybe I haven't clarified that very clearly here, but yes. So the rho here in principle. So this actually will become clearer if I describe an example. So I have an example later on. So maybe for now, let me just say that yes, you're right, and we think of rho here as being some tensor product of multiple states. Does that answer your question partly, at least?
Yeah, at least partially.
Okay, yeah. So I mean, okay, so maybe S itself is also going to be, it consists of S itself could be a tensor product. So we do in fact assume some kind of factorization here. So there are going to be multiple copies even within a single point.
Yeah, like basically it seems like, classically you had IID samples and then quantumly you should have the same, but like at least this equation doesn't look like IID.
Yeah. So yeah, exactly. So you are completely right. The most common settings that we encounter involve some kind of factorization inside S and rho, which captures the fact that the data is going to be many IID copies.
Okay, thanks.
Okay. So because we want to evaluate the data, and in the classical case, so if you had some training data, you could use it to come up with your hypothesis, and you could also use it to evaluate a loss function and further refine it. But in the quantum case, because most probably you're going to perform measurements, once the learner has used the training data, it needs fresh data in order to to test and evaluate the hypothesis. So this kind of forces us to introduce some kind of decomposition of the data space. So if the learner is using some data, let's say over some Hilbert space H data, it needs to implicitly think about some kind of decomposition into training and testing parts for this data. And this is the first subtlety that we encountered when we were trying to bring the classical work to the quantum setting. So it wasn't very straightforward to define exactly what generalization should be, because if you recall, we need to define a notion of empirical risk and a notion of true risk. And the empirical risk intrinsically depends on the training data. The true risk depends on some kind of unseen test data. To define this in the quantum setting, we're forced to think of the learner as having some kind of implicit decomposition of the data space into training and testing data. And I'll try to convince you in the rest of the talk that this is natural and perhaps the correct notion that we should be thinking of. And I also invite you to look at the paper for more discussion of why we think this is the case. So that's about the quantum data. And then what is the quantum learner? So the classical learner was a classical channel, right? It took a training data set S and it mapped it to some randomized hypothesis W. In analogy, the quantum learner is a quantum channel. And what is this quantum channel doing? It might perform a bunch of measurements on its training data. So of course, it might do some classical processing on the classical part of the data. And it might also perform some measurements on the quantum part of the data on the training subsystem. And then it might perform some post-processing. This could be a combination of classical and quantum post-processing. So once you do the measurements, you have some output states, post-measurement states. You can perform some post-processing on these post-measurement states. And at the end of all of this, it maps to some set of states over some hypothesis Hilbert space. So you start off with training data, and then you perform some measurements and some post-processing, and you end up with some hypothesis state. And that's just a quantum channel at this point. And the action of such a quantum channel of a learning algorithm on the input state rho, so this classical quantum input state rho, produces two things. So as in the classical case, there's going to be some joint distribution that the learner induces over classical data, the S part, and the classical hypotheses, W. So we want to conceptualize the learner as being able to produce both classical and quantum hypotheses. So in fact, one of the things that in our work, we didn't manage to come up with any good examples of this. We didn't manage to come up with any convincing example where the learner is producing a genuinely quantum hypothesis. The hypothesis always seems to be classical somehow. But when we defined and set up the framework, we were able to actually incorporate the possibility of a quantum hypothesis. So that's the sigma S and W here. And we were also able to take this into account while proving generalization bounds. So I'll come to that in a second. But so the most general action of the learner on rho produces a classical distribution, joint distribution over data and hypotheses. And it also produces a CQ or classical quantum output state. And this output state consists of two parts. It has the classical hypothesis, this is the W here. And it also has some quantum hypothesis that the learner is potentially producing. So is everything on this slide more or less clear? Are there any questions?
About those subscripts S, is this the classical data or the lambda and the POVM?
Yes. The capital S is the classical data set. Yeah. And yes, in the POVMs, the subscript S is for the data. Yeah.
I have some question.
Also on lambda, yes. This is also the classical data, yeah. So okay, yeah, maybe I'm using small letters to denote like specific data points and specific hypothesis points, and capital letters to denote random variables.
Yeah. So I also would have some questions. Maybe the question was asked before.
Mm-hmm.
I don't really understand even the first line.
Okay.
Because rho seems to be a function of S. Is that right? It says rho of S.
Yes, so rho can be a function of S, but it may not be, it need not be.
But the way it's written, it is.
Sure, yeah. I mean, we're allowing for this to be the case, yeah.
So what would it otherwise be then?
So for example, it could be that, okay, so in the example that I'm going to describe later on, so Scott Aronson's 2007 setting of PAClearning of quantum states. In that case, what happens is you have some classical data, which is going to be a bunch of observables, which are sampled according to some distribution. So the classical data there is going to be the description of an observable over, let's say, an observable on a d-dimensional state. And the actual state is going to be something that's independent of these observables. There's just, there's some state, underlying state sigma, and there are going to be many copies of sigma that you receive.
Okay, I mean, it might be independent, but like then it's still a rho of S is still the correct notation. And then it's I'm just very confused about your notation. It says like rho is 2, and then it comes like.
I'm sorry, I couldn't hear you, the last part.
Sorry, it just says like if I read the first line, I can't follow, right? So if I read the first line, it says rho is equal to. Right?
Oh, I'm sorry. Okay. Yeah, this is really bad notation. Yeah, okay. So I should have used, let's say, sigma here. Would that be, is that what you're pointing out?
Sure. And then the next line where mu is classical data, and then it would also say sigma of S.
This should say sigma. Yes. Yeah.
All right, but if I'm getting S, I can always compute rho of S. Sigma of S.
Right, you can compute sigma of S. You could perhaps, okay, you may
So
or may not be able
to. The quantum data I'm receiving is sort of like an additional add-on.
Yes, so for example, the sigma.
I could in principle compute myself.
Not necessarily.
Yeah, not necessarily, because sigma could be some very complicated state that even though you have, so for example, what could S be? It might be a circuit that describes sigma, but nevertheless, you might not be able to perform this circuit efficiently.
S may not be classical description of some classical thing.
What is my learner supposed to do? It's supposed to learn mu.
No, okay, so at this point, I've not really defined what the learner is supposed to do. This could capture a variety of settings.
Okay, but thanks.
Excuse me. So does that make some sense at this point?
No, I'm sorry, I just don't get it. But it's okay. I mean, maybe you continue and we'll ask later again.
Okay, sure.
Honest, okay.
Okay. Okay, so I just want you to keep in mind essentially the last couple of things here. So there is a joint distribution over classical data and hypotheses, and excuse me, there is a classical quantum output state, sigma. Okay. The next thing we need is some notion of loss. So as we had in the classical case, we need to be able to evaluate how well the learner's hypothesis performs. Sorry, I just need a minute to clear my throat.
You can get some water.
Yeah, I might actually do that. I'll take a minute. Thank you.
Promise.
I would just think that this rho should be like a tensor power state, like some sigma tensor n. That would make sense.
But I mean, the S, the E,
and the sigma.
the S itself would then also be some kind of like, right? The S is already distributed, and depending on the S is just because the S is the whole like n letter. S is like n letters, some gigantic alphabet. And then the rho should also be like letter dependent for each letter. Like, yeah, okay. I guess in this notation, shouldn't this like proj S be like S1, like proj S1 up to proj Sn, tensor rho S1, rho Sn. Is that what?
Maybe we should move on and then we can.
Let's move on.
Yeah, I'd be happy to talk about that probably on my last slide where I try to present an example. Okay, so moving on. So we have this learner, which is a channel over training and testing data. And the output is going to be hypotheses. But because we had this decomposition into training and testing data, and we don't use the testing data until the testing phase, this is just going to go along. So the learner's hypotheses live over this tensor product Hilbert space of testing and hypotheses. And then in the classical case, we had loss functions. We have to promote these to loss observables in the quantum case because we have a combination of classical and quantum data. So these are, as you might imagine, there's just going to be observables that potentially depend on the values of S and the hypothesis itself. And these observables are somehow going to, lead to a notion of loss. And exactly how do they do that? So in the classical case, we had, we could just evaluate the loss on the sort of input point. Now in the quantum case, this is the expected true risk. So let me break down this for you. The expectation that we're taking here is of a trace, and the trace itself is actually an average, right? So in the classical case, if you recall, we had, maybe let me write this down here. Yeah, so, whoops. Ah, I see. I can't annotate the screen somehow. I see. Okay, I can't annotate the screen, so maybe I'll request you to remember this. But we had this quantity R mu of W, which was the expectation over mu of the loss of the hypothesis W. And here in the expectation over here, what we have is the analog of that quantity. So this thing here, the trace over the state row test tensor sigma hypothesis, is the analog of R mu. And then we're taking the expectation of this R mu over this, because this is the true risk, we have a hypothesis that's been produced in the training phase. And then we have a new independent data point that's sampled according to the underlying distribution. So this expectation here is, as we had in the classical case, this represents this product distribution. So we have independent copies of S and W. And the quantity inside also has this tensor product structure. So there's two kinds of decoupling happening here. And this is the expected true risk. So we have the expectation of the product distribution of the trace of the loss observable evaluated on the product state.
Sorry, why does the test set depend on the previous data? Shouldn't it be completely independent?
No, because the test set, as I set up on the previous slide, the test set is part of this data itself. So again, yeah, my notation's a bit bad here. So it should have been sigma to begin with. And then it should also capture the fact that, as someone in the audience was saying, it should, in principle, in most cases, we're going to think about this being multiple, IID tensor copies. But yeah, but in general, this can depend on S. The test set can depend on S. In the specific example that I'm going to describe later, so PAClearning quantum states, it's not going to depend on S. It's just going to be tensor copies of some fixed state sigma. But in general, it can depend on S. An example of where it can depend on S is state classification. So if you had training data that is, let's say there are two possible kinds of states, psi1 and psi2. And what you're receiving is classical quantum data that consists of a state and a label. So there's the classical part is the label, the quantum part is the state. So S is the label. And the state itself now can depend on this label, right? Because if you think of the mixed state that represents the whole data, it's going to be a bunch of states phi. Each phi is going to be either psi1 or psi2, and it's going to be associated with the corresponding classical label. Does that make some sense?
But you have one label, one training quantum state, and one test quantum state that depend on the same label. Like for each S.
Yeah. No, this is absolutely true. Yeah. Again, this is because of my terrible notation. So the S here should be sort of, that there's like S subscript test and subscript train. Yeah.
Oh, you mean this S is just a set of labels? It's not the whole test, the whole training data.
This S is not the whole training data. Yeah. Sorry about that. Yeah. It corresponds to the test part of the decomposition. So on the previous slide, when I said that there should be a decomposition of the data space into training and testing, this is also for the classical part of the labels part of the data.
Yeah, because like here, S was the whole data.
Yeah, that's right. Yeah. Okay, so we have these two quantities now. So I haven't introduced the second quantity. So we have the expected true risk, and this is the analog of the classical expected true risk. And we also have the expected empirical risk. So again, my hat is denoting the fact that this is empirical. And again, yeah, the terrible notation, but this should have been, I should probably have used mu here to stress the fact that the true risk depends on the true underlying distribution mu. And I should have used rho here to denote the fact that we're getting some limited number of samples from this underlying distribution. And as in the classical case, we now have an expectation over the joint distribution. So the contrast between the true risk and the empirical risk, once again, is the fact that in the true risk, the distribution that you take an expectation over is the product over the data set and the hypotheses. And in the empirical case, it's the joint distribution that's induced by the learner. And inside, we have what you would expect. So it's the trace of the loss observable against the output state of the learner. So I'll just flip back to the previous slide. The output state of the learner, once it's done all its processing, it has these sort of classical data parts that has been, it's post-processed that data, but the data just goes along for the ride because it's classical. It's produced some quantum hypothesis, which comes from all this combination of classical and quantum post-processing of the quantum data. And it's also produced some quantum hypothesis, classical hypothesis. And this is the analog of the the classical joint distribution. Well, it's not just the analog. The classical joint distribution is still here, but in the quantum case, you have this new thing that pops up, this new output state of the learner that's also joint. So it's like it's a state that has these correlations between the data that was received in the training phase and the hypothesis that's been produced at the end of the training phase. So this is the empirical risk. The trace of the loss observable against the output state of the learner is the empirical risk. And we're taking the expectation of that over the joint distribution. So these two quantities are sort of central to the whole, the setting of generalization. So our the first thing we do in this paper is to establish this framework and then motivate the definition of these two quantities. So one of the reasons why we argue that these are the right definitions is, of course, that this reduces to the right classical notions. So if you take if you take the correct kind of settings for the data, if you make it all classical, then these reduce to what you would expect in the classical setting. And in addition, we have a bunch of examples that motivate exactly how quantum learning algorithms can fit into this framework, and exactly they reproduce the right kind of losses that are usually used in quantum learning algorithms. Are the quantities on this slide somewhat clear? Are there any questions?
One question. According to your notation, the R hat is the training error.
The R hat is the training error. Yeah, that's right.
Which should not depend on any test data. It should only depend on training data.
It should only depend on training data. Yes. Yeah. Again, yeah, this is because of my, because I've neglected to say that S is actually broken up into S test and S train. Yeah.
Yeah. And this is my question. So there's one Hilbert space called H test.
Yeah.
Which is still inside this equation. So there's some training data in the Hilbert space test.
Yes, that's exactly true. And this is one of the subtleties that actually arises in the quantum setting. So when I show you our generalization bounds, they'll actually turn out to be looser than they are in the classical setting. And this reflects the fact that in the quantum case, there's some extra sort of leeway that can be used by an adversary to fool the learner. So the fact that this testing data, the fact that the learner has to make, it's forced to make this, it's forced to earmark some part as training data and some part as testing data, makes it prone to some kind of, attack where the training data and the testing data are entangled or correlated in other ways, and this affects its generalization. So yeah, sorry, the answer to your question, I think, is that you are right. There is this other Hilbert space H test, and sigma has some part over that Hilbert space. And the fact that the state could have correlations across these two spaces is in fact important. Does that make sense?
Yeah, I still find it very confusing that in the end you're putting your training data into the test Hilbert space to evaluate the loss function, but I guess that's my
no, we're not putting the training data into the test Hilbert space. What I'm saying is just that sigma lives over test tensor hypothesis, right? So the S here is over the S is just S test. But because sigma started off being, so if we go back here, sigma is the output of A acting on rho. And because A had these two parts on training and test, when it goes along in the process, at the end, you have some part that's, that's just still, it maintains all the correlations with train. That's okay. Actually, maybe okay. That's maybe a better way of doing this. So I have a cartoon that sort of tries to capture the whole process, and that should be my next slide. So let me see if this makes anything a bit clearer. Okay, so let me just say that this is our definition of the generalization error. So the classical generalization error was the difference between the expected true risk and the expected empirical risk. And this is the new sort of notion of quantum generalization error that we've proposed in this work. But yeah, this at this point is just a definition. And I hope it's at least intuitively in terms of the, without going into the granular details of the actual definition of R hat and R, I hope like this is intuitively what you would expect to have seen based on the classical background. I think my cartoon should show up next. And yeah, okay. So what I'm trying to say is the following. So we have some data. The data consists of these zi's and rows. And the learner makes some implicit sort of factorization. It thinks, well, not factorization, but it makes some implicit split of this data into a training system and a testing system. And there could be correlations across this training and testing system. So the quantum part of the data could have some correlations, which could even be entanglement. I haven't drawn a squiggly line here, but the Z could also have some classical. So the Z is part of the classical data, right? So there could be some classical correlations across these. And then what does the learner do? It uses the training part. So it performs all of its learning operations on the training part. It has to measure the quantum data. That's probably necessary. And then it can perform classical post-processing on both the classical part of the data and the measurement outcomes. It performs some quantum post-processing of the measurement, the post-measurement states. And all of this leads to some hypothesis. So there's some combination of classical and quantum hypotheses. And then when it wants to test this hypothesis, it has to use the testing data because it's lost in the process of learning, it's lost the training data. So it needs to use the testing data. Because the testing data had some initial correlations with this state, with the training part of the state, there are going to be some correlations that persist between the hypothesis and the testing data. And then when it evaluates the loss, so it evaluates these loss observables, it estimates whatever the expectation values are that it needs to. The risk, the notion of risk that comes out of this process is the training risk. So it's like I was saying earlier, in the classical case, you have some training data, you produce some hypothesis, and you define the empirical risk using this training data. Because this was classical data, you could just reuse the training data and you define this empirical risk. And so there's intrinsically, it's empirical. In the quantum case, we can't reuse the data. We earmark some data separately for evaluating the empirical risk. But nevertheless, this is empirical risk. So, this data was part of the training set. It's not unseen data that's being independently sampled of the training process. Is this at least partially answering some of the questions that came up on the previous couple of slides?
So you're calling what you put in the test system, you call it training data?
No, I'm not calling it training data. Well, okay. It's basically the data that was received at the beginning. It's not inference data. It's not being sampled independently of everything that happened in the learning phase. Yes, Arnold.
Can I just ask? I hope my connection is okay, that you can hear me.
Yes, I can.
Just ask, is there anything sort of beneficial that this process can do to the test data during the training phase that would make your life easier later when the loss is assessed, which if so would feel a little bit like cheating?
Actually, on the contrary, I think this process can, the fact that the learner is forced to sort of keep aside some of the training data is making it prone to poorer performance.
Well, there could be some sort of, like I assume there's entanglement here between the part that's being trained on and the part being tested on.
Yeah.
So you could imagine some sort of non-local correlations where during the training you can sort of affect like without signaling, of course, but you could sort of affect what happens to the part that's being tested on.
Yeah.
Does help you later when you assess the loss. Is it possible?
Yeah, so actually maybe I think in this process what I'm realizing is that my nomenclature and notation are a bit probably confusing. So I'm calling this the training system and the testing system. What I really mean is, so this is all still part of the training phase of the algorithm. So this test system is not what is going to be evaluated on at the inference stage. That's going to be new, freshly sampled data, which is independent of the training process.
Okay, then I misunderstood. Thank
So
you.
this part is just being used for defining the generalization error, because you need some notion of okay, so basically the notion of empirical risk in the classical case could reuse the data. So you only needed one data set for both training and defining the empirical risk. In the quantum case, you can use data for training, but you can't use this to define empirical risk anymore. So you need to sort of have two parts in the training data that are used to perform the actual training, and one part is used to define the empirical risk. So I think, yeah, I think my nomenclature is not very good, and we use this in the paper, but maybe there's a better way to call these things. Is that a bit more clear? So the actual the inference data is new. So there's this, what I'm calling test here is different from the inference data, the unseen data.
So the loss at the right-hand side of the screen, this is not sort of your final scorecard that you...
No, this is the empirical loss.
Okay, thank you. Thank you. That helps.
And the next cartoon, the next slide depicts exactly what you were asking about. So the true risk, or the final scorecard, is when you have some completely new test data. You have some unseen test data that's been sampled independently after the training process is over. So here, the sigma 8 test is genuinely just new data that doesn't have any correlations with the data that was used for training. And when you evaluate the loss of the hypothesis that was produced on this new data, you get the notion of true risk. So we have the empirical risk, which has all these correlations. So it's the empirical risk, fundamentally depends on the training data. Well, yeah, training data modulo the fact that the training data itself has these two parts. It has a training 1 part and training 2 part, which is what I'm calling training and testing here. By testing on this slide, all I mean is it's the it's the second part, or like the maybe the mini batch of the training data that the learner has set aside for evaluating its training performance. So once you've trained and produced a hypothesis, you want to evaluate the training performance. And that's the part that it's set aside for this purpose. And on this slide, we have freshly sampled data that's independent of the whole training process. And this is being used to infer or predict some new, some new value. So this is the way we're conceptualizing, a quantum learner, basically, or a learner that uses a combination of classical and quantum data. So are there any questions at this point? So I think I'm already over time, right? How much more time can I take?
I don't know. I guess present your results. It's
okay. Yeah. Cool. Thanks. Yeah. So our second contribution, our main result, is to bring all this theory of generalization error bounds using information theory to the quantum setting. So with this definition of quantum generalization error that I showed you a few slides ago, if we assume some conditions on the loss observables, so we want the learner and the loss observables to be nice, so they have some good behavior, some kind of smoothness conditions on the tails of the distributions. If we have those conditions, then the generalization error of any quantum learner is going to be it's going to be boundable in terms of some information theoretic quantities. So as you would expect, there's one term that's purely classical, because we are sort of the way this model is a strict generalization of the classical model. So it captures classical learners, and there should be a classical term. This is purely the classical mutual information between the classical data and the classical part of the hypothesis. But there is something genuinely new going on. So we have an additional term, and this additional term has two parts. So as I said, this is the classical mutual information. And the additional term is capturing everything that's happening in the quantum case. So there is a quantum mutual information term. It's an expectation over quantum mutual information. So sigma is the learner's output state. In the learner's output state, there are two parts. There's a testing part and a hypothesis part. So there is some quantum mutual information between these two across this bipartition for this state. And that's going to figure in the generalization bound. And the second term is perhaps a bit more exotic. It's the Holevo information. And this somehow measures the amount of information that's accessible, that's classically extractable from the post-measurement states. So at the end of the learner's training phase, it's left with a bunch of states. And yeah, without going too much into the details, this term is capturing what those post-measurement states say about the hypothesis. And both of these terms, they appear in some under the same square root, and the classical mutual information appears separately. We have some examples. So each of these terms is in fact necessary. So we don't have a proof that the inequality is optimal, but we do have examples or rather we have examples where we can phrase the same example in different ways. So we can view the same example in different ways. And it turns out that each of the three terms is necessary because you can, for example, you can take the example of PAClearning, classical Boolean functions from quantum data. And by representing this, by using different kinds of input data to represent this situation, we can show that each of these three terms separately captures what you expect to happen, and the other two terms would be zero. So this is our sort of main technical contribution in this work. So after setting up this whole framework for generalization, we proved this information-theoretic generalization bound. Going back to this figure that I had earlier on, so Xu and Roginski's bound had this decoupling step, right? So there was the expected empirical risk and there was the expected true risk. That table was simpler because there was only classical data. So there was expected empirical risk for classical data. And in order to talk about the generalization error, there was this decoupling of data and hypothesis that was happening. In the quantum case, because we have both quantum and classical data, there are multiple decoupling steps. So the quantum part of the data has to be decoupled across the the quantum factorization of the Hilbert space. And the classical part also has to decouple. So the classical part, that's the second step that I've indicated here, that gives rise to this classical mutual information term. And the quantum decoupling step gives rise to the quantum mutual information and Holevo information. And the way we prove all of this is sort of we use the variational characterization of the relative entropy and some quantum information theoretic tools, essentially. And yeah, I invite you to look at our paper if you're interested in that. So what are these bounds good for, and what is this framework good for? We've been able to apply it to some settings of quantum learning. So most importantly, the first thing that we did was perhaps some sanity checks. So we get, so if you consider the pretty good state tomography idea from Scott Aronson's 2007 work, where he was thinking about PAClearning of quantum states from measurement data. We get some, we can recover the sample complexity bounds from that paper, but in fact we get sort of information theoretic tightening because we can recover Aronson's bounds by upper bounding the upper bound that we have using, the dimensions, as I was saying earlier on in the talk. But in fact, the actual information theoretic quantities are perhaps they give a more sharp bound if you can evaluate them. And then we were also able to work out some average case sample complexity bounds for learning measurements that perform state discrimination or classification. So to the best of our knowledge, these two works that discuss state classification, they don't phrase this sort of in-expectation bound explicitly. So this is something we derived that's somewhat new. And then recently, there's been a lot of work on quantum differential privacy. So if you have a quantum channel that is differentially private, then we also get generalization guarantees for such, for such channels. And this is something new that we've been able to get out of our bounds. So I think that's, yeah. So this is my example. Maybe I'll skip it in the interest of time. I can come back to it once I finish if anyone's interested. So to conclude, we have this new sort of framework that's useful for analyzing learning from quantum data, and in particular for describing how well you can generalize when you learn from quantum data. While our framework does capture a wide variety of settings, it doesn't capture everything. So there are, so classical shadows and shadow tomography, for example, are some very important kinds of learning problems that our framework isn't quite able to capture, or rather, you can shoehorn them into our current framework, but we're not able to recover the same guarantees, the best guarantees that are known for these learning tasks. And we have these quantum information theoretic generalization bounds. And classically, as I pointed out, there's been a lot of follow-up work, and it would be naturally, interesting to see if some of those things carry over to the quantum setting, in particular, out of distribution generalization. So if the testing data is coming from a distribution that's drifted away from what you trained on. And then we have these proof of principle applications, and amongst the 3 applications that I pointed out, we've recovered some bounds from existing work. We are able to prove some things that weren't explicitly stated in previous work, and we also get 1 or 2 things that are genuinely new. But what would be really interesting is if there are actual well-motivated examples where the learner can produce some kind of quantum hypothesis as well, and whether these information theoretic bounds can lead to concrete and novel bounds for generalization in those circumstances. So that's essentially what I wanted to say, and thanks for listening.